Thanks. I guess that came from the PR department at Recon. Kind of sounded like a commercial, but I'm not going to try to sell you any products today. So as Nick mentioned, I do work in wearable computing and specifically in direct-to-eye technologies. So I'm going to spend a little bit of time today kind of setting up a pivot into describing how I think direct-to-eye technologies are going to make changes in the way we interact with things. It's something that's not actually too different than the pivot that you all just underwent in the last several years when you started moving away from things like this to smartphones. And so it's a pretty similar evolution. And I think actually if you trace it back over a longer time period, you can see that evolution is actually pretty continuous, starting in the 1950s, getting to today. And from there, I want to project out just sort of my notion of what a cyborg is actually going to look like a little further out into the future. And I think that that notion, for me at least, is pretty different than the notion I would have had when I was, say 17 or 18 years old and I was just about to go to university and kind of embark on a career working in computing technology. A couple things. So one, I wasn't really sure exactly what the audience was going to be here. So I didn't know how technical the presentation should or shouldn't be. So before I start, it's not particularly technical, but I'm just wondering how many people either have a engineering or a science background in the audience? Okay, a good amount. That's good. For the rest of you, I'll try to make sure that if there are any terms I'm using that I think might be a little fuzzy or not clear, that I kind of pause to explain those. Cool. So the evolution of computing. So I just mentioned that computing is something that I think has actually had a fairly continuous evolution. It's not a linear evolution, it's actually an exponential evolution, but if you just sort of look at the trend, it's a pretty continuous trend along an exponential line. And this actually doesn't go back 50 years or 60 years, but these are all pretty familiar looking form factors to you for what is essentially the same machine. Computing actually hasn't changed all that much during that time. The core innovations for computing were things that happened, one in the 1950s, when the silicon-based semiconductor was invented, or at least commercialized, and that was done at combination of Bell Labs and Texas Instruments, and that was in 1954. And then the next big one was really the advent of the internet in the 1980s. So there's really only been two huge innovations in computing in the last 60 or so years. The rest of the things you see are innovations, but they're really at the engineering level. They're ways of doing the lithography at a deeper level so you can get smaller and smaller transistors and things like that. And they're awesome. They're the things that allow you to have a smartphone that can do everything it does and connect that smartphone to the internet. But at heart, it's really doing the same sort of thing. So, along the way, there have been two major trends, right? So the one is the miniaturization that I just described. The other one is what I would call distributed computing. So that might be a little bit of a sticky term. So what does distributed computing mean? It's actually pretty simple. It means that you accomplish computational tasks, things like rendering up a screen or whatever it might be, in different places, different physical locations, and at different nodes, and then you bring that together into the total solution. The simplest example of distributed computing is you interacting with a website. When you interact with a website, you've got a computer or a smartphone or something like that with you, and then there's a server off somewhere else over the internet. You have actually no idea where that server is. In fact, the people who even loaded that website may have no idea where that server is, probably don't have any idea where that server is. You send a request over the wire, some computing happens in some far off location that you don't know about, and it sends you back a bunch of CSS and rich HTML and other things like that your computer takes and then produces the images that you see. So this is an example of distributed computing, and almost all the computing we do today is done that way in some form or another. It's all connected. So the last slide had a question mark, and the question mark was, what's next, right? What's the next thing? And you may have already inferred what I think the next thing is. And that's wearable technology, but it's almost not even really next. It's just sort of next to get really popular because it's already here. These numbers are probably pretty conservative, that it would be about 1.5 billion next year in total sales. Before coming to Recon Instruments, actually worked on a couple of these products. I worked at Nike, so I worked on the Field Band and the GPS Sport Watch when I was there. And these products sell very well. People are very excited about them. They don't have the adoption that you see in smartphones, but the smartphone has been I think it'd be hard to argue, the fastest adoption curve of any technology device in the history of the world. And I would say that you're going to see a faster adoption curve with these wearable computers than you even saw with the smartphone. It may be hard to believe, but I think you will. Whether or not it'll peak out at the same gross numbers across the world is a different story, but the rate at which they're going to get adopted is faster, and it is currently faster today if you just look at what's happening with those wearable technologies. So these are wearable technologies. I mentioned I work on a couple, and there are others that are coming up. A couple that have been touched on a little bit today. The ones that I work on today do something different than the ones on the previous slide. They give you information direct to eye. The one that you've probably all heard of is Google Glass. There are actually several others on the market aside from the ones that we make at Recon. They look like, it's kind of hard to see, well, you can see how ugly that one is. That one, it's a little harder to see how ugly it is, but it's pretty ugly. This is, I hope there's nobody here from Vuzix. This is the Vuzix M100. It's got a band that goes over top of the guy's head. So that's not very good. It kind of looks like headgear or something like that. But the principles are good. The principles are pretty solid. It's just not something you would wear that would make you look good. Google Glass is debatable. Maybe you think it makes you look good. I don't particularly like how it looks, but maybe that's because I work at Recon. We'll see. But one of the things that hinders adoption for any device is when it's not something that you can be proud to own. And so, although there's a lot of good technology there that does direct to eye, we haven't taken the next step. So I'll give you a hint of what I think the next step might look like. There may be some company somewhere in the world working on a device something like this. It could even be pretty close to here. And I think when we get to devices, you can't actually see all the detail in this picture because it's a little washed out. But I think when we get to devices that look more like this, you're going to see direct-to-eye technology expand in its adoption. I don't think that it's going to be in the very near term that I would be standing giving a talk like this, and that you'd all be wearing something like this and looking at me and getting text messages at the same time or anything like that. But I could see a world where you were biking or running, or it had a clear lens on it and you were wearing safety glasses while working or something like that, and you were using this. And that's a world that I think is not too far away. So since I work at a company that produces microcomputers and heads-up displays, I often get the question, why use a heads-up display? Why do I need a heads-up display? This is a mock-up of what our current heads-up display for action sports looks like, and we use it mainly in the ski and snowboard markets. And as a user experience, it's pretty awesome. I don't know if any of you ski or snowboard, but if you do, you can pop by the office in Yaletown sometime and I'll lend you a goggle. And you can try this out. And it's a different experience. It brings another element to something that previously didn't have a connected digital experience to go along with it. You can see how fast you're going. You can see where your friends are on the mountain. You can see where points of interest are. You can find the bathroom. Where is that? What are the best restaurants at the mountain? You can do all these things that you couldn't do before. They enhance the experience in a way that just wasn't present. So a typical use case would be for a parent to track their children. The parent wants to ski on runs that the kids can't, but they don't want to lose their kids for the entire day. They want to know where they are. Well, you can do it using technologies like these. So they both bring an experiential element, and they also bring a very functional element, and I think it brings real value to people. And because it brings real value, you're going to see people use it. There will be adoption, and I think that that's one of the key markers in my career when I look at products that I want to work on, products that I don't want to work on, or products that I want to work on but I want to change them. I always look at what I need to do in order to bring real value to the user, not just apply something that's really cool. I mean, it's really cool to be able to power a micro LCD with a heads-up display and have this miniaturized computer, but if it doesn't drive real value, it won't get adopted. And I think we'll see that coming out with the latest generation of products pretty soon. At least I hope that my products will do that, or our products will do that. Other than that functional aspect, if you look at, or I guess perhaps a killer app functional aspect of direct-eye technologies is speed. So if you just think about what that means, the trends I talked about earlier, really what they have done for computing is bring speed to computing. They brought speed in a couple of different ways. So some of the ways are, they compute faster, much, much faster than they used to. And that's an exponential increase in computing power. And that means that there's a bunch of things that means, but probably the most important is that you can work with very large data sets. You would not have been able to do the kinds of things Mike was describing for the tsunami warning or real-time tracking of who's outside your door that you know or don't know without giant data sets being processed by computers. And those are done today by Facebook or Google and a few other companies. And they couldn't have done it without speed. So although the computer doesn't do anything different in principle than what it did before, the ability to do it very fast allows them to use different methodologies to process data, and that brings you all the things you see today in real time. They can access and cache extraneous data on the fly. Let me explain that one a little bit more. The fact that they're connected means they don't have to have all the data they need on board. If you had to have all the data you needed on board to do things, it can be very difficult. Where do you store it? It gets harder to compute against it. You store the data that you need maybe locally so you can get it very fast, but at any time that you don't have the data you need, you can go grab it. And that connected aspect that I described earlier has enabled computers to do this. And so now they can do these things very fast. You can imagine if that wasn't the case and you didn't have that, and I say, well, I want to compute something and the computer doesn't have it. The only way for me to do it in the past was for me to go get a floppy disk, pop it in the computer and get the data there. The trip time it took me to do that means, and then coming back and loading the data and getting it to the computer, I might get the answer, but I'm probably not going to need the answer by the time I get it if it's something like the use cases we were just describing. So the fact that they're connected is all about speed as well. The next one is they go where you do. So probably everybody here has a smartphone. You have a computer attached to you that's connected and that's small. And because they go where you do, you don't have to wait till you get home to see an email or get a text message. You don't have to wait to tweet out about what's going on at this conference if you're interested in it. And that's about speed as well, because it just means that there's less delay time. It also means that you'll probably do it more. When you look at wearables, it's even faster. And you may not get the same giant increases that you're seeing when you look at like the big server back into Google and what it can do for you with like things like navigation or Foursquare and check-ins, but it can be pretty fast. The fuel band is a good example. I worked on the fuel band product, and the first question you would get if you were talking to a consumer focus group about the fuel band was, by the way, the fuel band is a Nike product that tracks your activity with an accelerometer and a wristband, and I'm embarrassingly not wearing mine today, but although I worked on it just a year ago. But people would ask, well, why do I need that? Why can't I just do that with my smartphone? And the difference in time for you to be able to quickly see how active you've been, whether you're about to reach your activity goal for the day, whether you need to go for a walk at lunch, or whether you should consider taking a run after work, or whatever it might be, or whether you want to take the stairs that moment versus taking the elevator, actually makes a real difference. And it's that very fact alone that has the fuel band selling over 1 million units to people just a year after it was released. And there are many others as well, Fitbit Flex and the Jawbone Up and so on, which aren't actually as good at giving you real-time information, so you might want to consider that if you're ever buying one. So let me take the speed advantages down even smaller. So that one's pretty fast, right? I mean, I could also have a smartphone tracker. I could pull the phone out of my pocket and look at it, but you're not going to do that all the time during the day. You're going to do it less. And it's because it takes longer and it's more intrusive to your experience. So that small difference in speed matters. I want you to think about direct-to-eye technology. Sorry, let's bring this back up. And to think about cycling. So in cycling, every 5 seconds that a rider looks down, so let's say they had a bike computer on their bike. Every 5 seconds that they look down, they lose 0.2 seconds of time on average. So because of the aerodynamic drag that they get from getting on aero. It's a small amount, right? So we're not talking about a giant speed advantage here. But if you're an Ironman athlete, or if you're riding in a very long race, that makes a difference between whether or not you're going to win or you're going to lose. So it's pretty important. And this is just one. There are a few others, weight savings and other things you can get with wearable computing, but I just didn't want to go through the whole list. I think even more important than those little minor tweaks is that having instant access to the data when you need it and how you need it can push you, and it enables you to perform optimally. So if you look at races, especially for people that are non-pros, because sometimes you'll see a pro that's just so much better than everybody else, they're pushing their envelope every time that they're out there. But for the most part, for most people, even very, very good riders, their personal bests are usually set when they're in competition with somebody. And that's done because it's pushing them. And you can't always be in competition with somebody if you don't have something to help you do that. You can't always be riding with somebody who's riding at exactly the same level. And so having this data can enable you to do that. The edges you get from that might be small, but it's truly a game changer when you're at your limits. So if you are at your limit personally as a recreational athlete, or at your limit as a pro and you want to push it further, these things make a big difference. The way I would summarize it is, when it comes to speed matters. So if you really want to push it the limit, and I'm talking about sports here, but this applies in many other places as well, speed matters. And even if you're getting incremental increases, those incremental increases can make a big difference to how you actually perform. So I'm going to give you a concept of what this might look like. That's Tom Fowler from Recon, and one of the guys from my team, who you can't see them right now, but they're riding with sunglasses that have a heads-up display in them, and testing them out on Cypress Mountain, which is why it's snowy in the background. So what they might see: you're riding and you're able to see your power output, that's what's in the middle, watts, your speed, how fast you're going, and your RPM. If you're a rider and you had to constantly look at another device in order to get these things, you're not performing optimally. In other words, the two things are mutually exclusive. You can't, in order to perform optimally, you need to know this so you can try to stay in your target zone. But in order to know it without a direct eye device, you have to look down, which means you cannot perform optimally. You have to get distracted, you have to get out of position. So that would be mutually exclusive without that kind of thing. I talked also about being able to be pushed. So what if you're riding alone? You're not going to be able to ride with somebody all the time. But with a connected computer, that connects you to either data that has your last ride, or the ride that your friend did this morning because you guys couldn't line up your schedules, and you can compete against that curve in real time and try to beat your friend even though he's not there. That can push you in ways that things couldn't before. So to me, those are game changers, and they bring real advantages to people in the real world. And although we have a lot of stuff that we do today with our existing devices, they can't do this kind of thing. And so there are real advantages there. Cool. Okay. So I guess the next question is, so I mentioned the evolution of direct eye devices and wearable technology and how that sort of evolved over the last 60 years or so. And then I said I was going to project out from there as to what I thought was going to happen in the near future, and then eventually what that says about what a cyborg might look like some years from now. What I think is going to be happening over the course of our lifetimes and our careers, just looking at the average age of people in here, let's say the next 20 years, is you're going to see true applications of nanotechnology. You may not have machines like this. This is a visual conception of what a nanotechnology device might look like. Those are red blood cells, and that's a device about the same size. A red blood cell, I don't know if this is, people know the size comparison. A red blood cell is of the order of maybe 3,000 micrometers, so very small. So you could have devices like this inside your body. And a device like that inside your body could do a lot of things for you. It could kill viruses or bacteria that would be harmful and bolster your immune system. It could clean up cholesterol. It could clear arteries. It could do lots of other things if it was properly programmed. But it would have to be pretty smart. You wouldn't want to turn one of these guys loose without a very good brain inside it, or at least without a very good programmer's brain, instructions being codified inside the device. So we need to get there. I talked about miniaturization as a major trend. So the question might arise, when do we get there? When do the computers get small enough in order to do something like this? Has anybody in the room ever heard of something called Moore's Law? If you have an engineering or science background, you may have heard of this. So for others, Moore's Law is actually not a law at all. Which is why I say Moore's Law is not so binding or legally binding. It was actually just an observation that the founder of Intel, one of the founders of Intel, Gordon Moore, made in 1965, I think it was, quite a long time ago. And there's many different formulations of it, but the core that he was talking about was miniaturization of these transistors I talked about earlier. And he said that every 18 months, the number of transistors that you could fit on a particular area doubled. And so as the number of transistors you can fit in an area doubles, computing power roughly goes up linearly with that. And the amount that you would need commensurately shrinks, right? The number doubles, it means they're half the size. So this is actually held to be remarkably true for the last 50 years or so, 40, 50 years. And there's probably many reasons for that. Probably one of the reasons is that industry cycle sort of oriented around it. So aside from any physical reasons why this was happening, you just sort of planned for your processor needing to be half the size. And so AMD and Intel and so on just did that. But there are other reasons too that have to do with sort of the raw physics there. But it's not so binding. It's not, like I said, it's not a law. It was more of an observation. This is a quote from John Gustafson, who is the chief product architect at AMD, who is the chief competitor to Intel. I think this was in 2013. He said, you can see how Moore's Law is slowing down. We've been waiting for that transition from 28 nanometers to 20 nanometers to happen, and it's taking longer than Moore's Law would have predicted. I'm saying you're seeing the beginning of the end of Moore's Law. I believe this is true as well. You'll hear a lot of people talking about that, but there's a caveat. It's true of silicon-based computing. So that, I mentioned that revolution that happened in 1954. For that technology, I think that this statement is true. So the current prediction is that, and I think you can actually see the effects of this today, and it's true not because of engineering, it's true because of physics. So the physical laws are binding. You're not going to be able to get around them. And there's two major physical reasons why I believe that this is going to be true. When you get down to sort of the 5 nanometer scale, which with current predictions would be happening around 2018 or 2020, depending on who you talk to, at a rate much slower than it's happened so far. The one physical reason is the quantum uncertainty principle. So it sounds kind of very complex, but you can sum it up pretty easily for the purposes of this by saying that when they get down, when the size of that connection in the transistor gets down to just a few multiples of the radii of the electron that's inside, and of course electrons inside the computer are what are doing all the work, you can't be sure that that electron will actually stay in the wire that you have it in. The quantum uncertainty principle says that there is a probability, and in this case of those small scales, actually quite a high probability that it'll jump right outside there. It's called quantum tunneling. So if that happens, your computer's not going to give you the right answer because the signal that was supposed to be transmitted inside didn't make it. right? Or it made it in the wrong place and it's going to go haywire. So that's one reason. The other reason is thermodynamics in physics, and it says that things are going to be very, very hot if you go too small. Basically, you'd be frying an egg on any machine you have, or it would burn a hole through your skin. So for both those reasons, I think that that's going to be true for silicon-based computing. And I think you can actually see this in effect today. This is charting back from 1989. The size of the silicon semiconductor. This is actually the size of what they call the manufacturing process. I won't go into the details of the engineering there. So it's not the size of the actual connections. But anyway, you can see that it was dropping off very quickly in 1989. It dropped off even faster than that before. And it's starting to trail off. And it's been trailing off for a while. And the reason I say you can see this effect in your own computers is because I bought this MacBook Air just maybe 5 months ago or 6 months ago. And it's not much faster than the previous generation that I had, right? They've made some tweaks and it's a better machine. But they haven't been able to keep up with that arms race where before, every year that you bought a machine, it was roughly double the computing power, or at least double the CPU clock speed, which should translate to computing power sort of roughly. So you can see this happening today. It happens in your smartphones. It happens in your computer. It's slowing down. So I would argue that a revolution is needed in order to get to what I was describing before, those very small nanoscale machines. For point of reference, I should have mentioned what a nanometer is. Nanometer is a billionth of a meter. And so if you wanted to get a sense for what that means, it would be roughly this, a nanometer to a meter is roughly the same as a marble or a cherry to the size of the entire Earth. So it's a very big difference. Or stated more whimsically, I heard somebody say this once, the distance of a nanometer is about the distance that a man's beard would grow between the time he grabbed his razor and lifted it to his face for an average man. So it's a very, very small distance that you're talking about, a couple molecules long. So in order to get down to those scales, you need something different. This is a visualization of what I think is going to be the next major advancement in computing. The thing that would be roughly equivalent to the transition from vacuum tubes and other types of of transistors into silicon-based semiconductors. And it would be a molecular transistor. And this is where you'd be using literally one molecule. This little agglomeration of green, yellow, and purple balls is a schematic of a molecule. And the idea would be, by the way, transistors are basically three connection devices. They're actually really simple. They control current, and then they have 3 nodes. So the idea is that the molecule would actually be connected as the nodes. And it basically switches current from going from one wire to another that are just composed of a few other molecules as well. And that gets you down to very small scales. And if you had transistors that worked this way, you could build machines like the ones I mentioned. There's lots of other engineering challenges to get over as well, but at least you would have the raw computing power that you needed if you could make a circuit that worked this way. So I kind of hope that that'll happen. Okay, so now I'm going to get into, I mentioned I was going to say what my conception of a cyborg might look like, maybe let's say 50 years from now or something like that, within a lifetime. So one thing that's interesting to observe, and this is opinion, so it's not necessarily my opinion, but there's a lot of people talking about this right now. You might have heard of it referred to as the Google effect. This is Gary Small. He's a research psychiatrist at UCLA. The current explosion of digital technology not only is changing the way we live and communicate, but is rapidly and profoundly altering our brains. I'll give you a couple examples, just very quick examples of how that's the case. And this happens to me, and you probably observe it in yourself. You outsource your memory. Things you may have remembered before, you don't bother remembering because it's on your smartphone. So for me, it's calendar appointments. I had never forgotten a calendar appointment in my life until I was maybe in my mid-20s. And by the time I was in my mid-20s, I was in the workforce. I had electronic technology to help me remember when my appointments were. And Outlook just popped up a reminder every time I had to go do something. So if for some reason that didn't work, or I failed to put the meeting in there, or whatever happened, I would miss the meeting if I didn't have the Outlook reminder. I had never missed a meeting or any kind of appointment before that because I always remembered. As soon as I said, yeah, 2 o'clock on Thursday, I just remembered that. And so this is referred to as outsourcing your memory. Rather than trying to remember the things that you need to know, you just remember how to access those things. You just know that on your smartphone is all your appointments. And it's analogous to the second statement, which is you solve problems differently as well. I remember when I was in university and I was in first year calculus, I was tutoring other first year calculus students, and all they were trying to do was remember how to do the algebra. And I was trying to explain to them how calculus actually worked rather than the algebra, but you're tested on the algebra. So they knew in order to succeed on the tests, they had to be able to do the algebra. But the algebra wasn't the important part of the calculus course, it was the calculus. You wouldn't need to do that anymore. It's really easy to look it up. If you had a problem, you can just go punch it into 1,001 different algebraic computers on the internet, and they'll just spit the answer out for you. So why bother remembering that? You can actually focus on the understanding. So you use your cognitive power for a different purpose. Okay. So we've got this world that has an internet, right? It's pretty connected. And that internet is expanding. It's not only expanding in the number of nodes, like the places that it reaches, it's also expanding in terms of its bandwidth. So the pipes are pretty fat, and they're getting fatter. Although you'll hear telecom say that the infrastructure is strained, that's really just because they're not very good at keeping up with the demand. But the technology is there to do all that stuff. This looks a lot cooler if you can actually see it. But anyway, this is a guy, obviously, as you can see. And what I think is going to be part of the Cyborg experience is going to be connecting to the internet direct to eye. And you kind of do this already with your own computers, right? You connect to the internet using your eyes. And you'll be able to do it at an even smaller scale, like I previously showed you. But I think really that's going to be the connection. You know, if I would have thought to what a Cyborg would have been like when I was much younger, I might have thought you might have some kind of implant to do this, right? So it's like directly wired into your brain. But why do that? You have an excellent optical interface sitting right on the front of your face. There's no reason to replace that interface. We don't have interfaces better than those, so there's no reason to do it. You can just do it this way. Maybe one day there will be, and maybe that'll necessitate a revolution there, but until it's functionally better, there's no reason for that. So you've got a great optical interface. And behind that optical interface, you've got a computing mechanism that is nothing like all the computers that we have that run the internet or that are part of the internet. They still can't do anything like what your brain can do, and they're not getting closer to it regardless of what you might hear. I don't know how many people have heard of the IBM computer Watson. Has anybody ever heard of that? Probably, I'm sure some have. So Watson's probably the closest thing that the world has seen to what we would call strong AI. At least some of the researchers that worked on it would say that. Strong AI is the notion that a computer could pass what's called the Turing test. It's a reference to Alan Turing, is kind of the father of modern computer science. The Turing test is essentially a test to see if you act like a human. And it's a test where you would have a barrier between you and something. You don't know whether it's a human or a machine, and you'd ask that something questions. And if after a while you were unable to tell whether it was a human or a machine behind there, you have to say that that machine, if it was a machine, has intelligence. And this is strong AI. Weak AI is what you see in video games and what Google has and things like that, where the algorithms and the data set that the computer operates on are so good that most of the time it can predict what you're doing. A simple example, type ahead in Chrome or Google search. You go like 3 letters in and it knows what you're about to search for in a lot of cases. It's looking at your location, it's looking at your search history, it's looking at the things other people search for, and it's looking at the most recent things that other people search for, as well as a whole bunch of other things. That's what they call weak AI, and computers are really good at that, but they haven't gotten good at strong AI. But you are good at strong AI, right? If you were behind that wall and I asked you a bunch of questions, I probably wouldn't think you were a machine. So it'd be unlikely I could stump you, but you could stump Watson very easily. You could ask Watson easy questions to stump it. If you ask factual questions, you can't, but if you ask simple questions like, hey Watson, if a really pretty girl asked you on a date, what would you say? He's not gonna know, because he can only reference a database that he has. He hasn't never had to address a question like that. They could code the answer up to that one, but then you just ask them a slightly different one and they won't have that either. So this is one conception, and I think that's the way it'll work. And then this person would have what I described earlier inside them as well. So they're connected to the internet via this great biological interface that they already have, and they have this great biological computer that does things that other computers can't do. And then they have these other computers inside them that are also doing things that their biological mechanisms can't do. So if you have a family history of heart disease or cancer or something like that, maybe you have a flaw in your biological system that you can easily correct with one of these computers. Well, the computer and the machine associated with it. And so, as I've gone through my career and my thoughts of what a cyborg might look like have changed, this is what I think will actually happen. And I think that's it.